This is video number 3 for electricity for Physics 11. In this video we'll finish up by talking about electric power. We'll also talk about another unit that we often use for electric energy, and we'll also talk about something called EMF and terminal voltage. And then in our last video, video 4, we'll talk about circuit analysis. All right, so I hope that you are familiar with the idea of power already. So really electric power just really refers to the application of, well, the concept of power to electricity. So specifically it is the rate at which electrical energy is converted to other forms. So of course, for example, whenever you plug something in that uses electricity, maybe it's your television, it's converting that electrical energy into sound and light so you can watch what's on your TV. If you're playing your stereo system, it's converting that electricity into sound primarily. So it's using electrical power and it's converting it into other forms. So you know that power is the amount of energy that's transformed in joules divided by the time. And the unit for power is, of course, the watt, named after James Watt, who helped improve the steam engine, and 1 watt is equivalent to 1 joule per second. So for electric power, so you have 3 different forms of an equation we can use. The first one is power is equal to voltage times current. So power is equal to V times I. But if we just take a quick look at the units, I think you'll see how it works out. So a volt, remember, is a joule per coulomb, and current is a coulomb per second. So if you take joules per coulomb times coulombs per second, you get joules per second, which is, of course, a watt. If we use Ohm's law, we can come up with a couple of other forms of this equation. So if we substitute in for V, I times R, we get power is equal to I squared times R. And if we substitute in for I, V divided by R, we get power is equal to V squared over R. So these are just 3 different, slightly different forms, or 3 different ways, I guess, in which we could calculate power. Here's a couple of examples. So again, you might want to try these examples. So if you want to do that, pause the video, try these examples, and then come back. And of course, I will go over the answers. All right, first example, what is the power output of a 9-volt battery producing a current of 0.2 amps? So power is just simply voltage times current, so 9 volts times 0.2 amps gives 1.8 watts. Second example, a current of 50 amps flows through a conducting wire with a resistance of 0.1 ohms. What is the power loss in the wire? The answer here is 50 amps squared times 0.10 ohms gives 250 watts. This might be a good point to mention that actually electric current, when we transmit it over power lines, typically we do it at quite a high voltage, and that allows us to actually reduce power loss in those power lines. All right, I also want to mention another unit that we often use for electric energy. So the unit that I'm going to talk about is something called the kilowatt hour. So it's basically the amount of energy that is produced or consumed in 1 hour if the power output is, or if the power is 1 kilowatt. So just to do a little conversion, so energy is power times time. So if the power is 1 kilowatt or 1,000 watts, and the time is 1 hour, which would be 60 minutes times 60 seconds per minute, or 3,600 seconds, we would get 3,600,000 joules. So 1 kilowatt hour of energy is equivalent to 3.6 megajoules of energy. Now, this unit that we use for electrical energy is commonly used by your energy provider to actually figure out what to charge you on your electrical bill. So here's an example. So let's say a 1200 watt hair dryer runs for 20 minutes. How much energy is used by the hair dryer in kilowatt hours? And if that electric energy costs 25 cents per kilowatt hour, what did it cost to run the hairdryer? So again, if you want to give this a try, pause the video and then unpause when you're ready to have a look at the answer. All right, so the energy is the power times the time. Notice that I've converted the power into kilowatts and the time into hours. So 1200 watts is 1.2 kilowatts. 20 minutes is a third of an hour, so 1.2 times a third of an hour gives 0.4 kilowatt hours. So that's the amount of energy that was used in kilowatt hours. And then to calculate the cost, we just take the number of kilowatts times the cost per kilowatt hour, and we get the answer of about 10 cents. All right, last thing I'll talk about in this video is something called terminal voltage and electromotive force, also called EMF. By the way, there's a band called EMF. If anybody can tell me what the song is by that band. Maybe I'll tell you at the end of the video, see if you know. All right, so electromotive force, or EMF, is essentially another term for voltage, but to be specific, it's the potential difference across the terminals of a battery when there is no current flowing through that battery or in a circuit. So it's like if you could just measure the voltage of a battery just by itself without any current flowing, that would be what we call the EMF. Now, why would this be different than, say, if the battery was in a circuit and if there was current flowing through? Well, the answer is that pretty much any device, whether it's a battery or a power supply or whatever it is producing the voltage, those devices will usually have some of their own internal resistance. And so when current flows, that internal resistance will cause a little bit of a voltage drop, equal to whatever the current is times that internal resistance. So that will then actually reduce the actual output voltage of the battery, and that output voltage is what we call the terminal voltage. Okay, so to give you an example, so let's say here's a battery, so here's our representation of a battery. So we have the EMF, or the voltage of the battery, just without any current. But again, if there's some internal resistance in that battery, and if there's current flowing, then the actual output of that battery or source will be the EMF minus the voltage drop through the internal resistance, which is equal to I times R. And we'll just give a quick numerical example. So for the circuit at right, find the current I and then the terminal voltage of the battery. So again, you might want to pause this, try this on your own first, and then unpause when you want to see the answer. All right, so first off, the total resistance of the circuit will be the 10 ohms plus the 0.5 ohms of internal resistance, so 10.5 ohms. So then the current in the circuit will be the voltage, the EMF, the 12 volts, divided by the 10.5 ohms, which would be 1.14 amps. Now then we use the equation that I gave you before, so the terminal voltage will be the EMF minus I times R, so 12 volts minus 1.14 amps times 0.5 ohms, which as you can see is gives us a final output voltage of about 11.4, so a little bit less than 12. There's a bit of a drop. And so that's what we call the terminal voltage.